Hi everyone, welcome back. So in the last video, we looked at the electric and magnetic field integrals based on the dyadic Green's function, which were these ones. So now what we want to do is I wanted to show you a demo of basically how you can actually compute these integrals in MATLAB based on some current distributions, right? And we'll show how essentially how it compares to HFSS, right? So for this, we will use HFSS, which we've done in the previous demos. So what I'll do is I'll open an example antenna, and we'll see why we're using this antenna. But we'll use this Potter horn. Okay. So let's open that up. And I've covered Potter horn before in the 6.5 hour video that I made on different antenna designs. You can go back and look at it there as to how it actually works. It's a really cool antenna. It's a very nice antenna for feeds because it has very low side lobe level for feeding reflectors and so on and so forth. Okay, so I recommend that, we can work with this one in today's video. So let me actually go ahead and save this. Once I save this file, I'll continue. So I'm done saving it, and we want to make a few changes. So we'll delete this radiation box. I'll clear all of these. And we want to change the frequency. So let's do 10 gigahertz, just because that's what we've been working with. And then go to coordinate systems, click on global, and we'll make a radiation box. So I'll make a physical box because I want to change the size of it every now and then. So I'll make this -50, -50, -10, 100, 100, and 140. Okay, so this is kind of close to the ideal radiation box that HFSS would have made. So I'll make it transparent and assign boundary radiation. So hit OK. Okay, that's my radiation box. And I'll delete the auto simulation. I don't care about that. And we'll add a new simulation. So we want to do this at 10 gigahertz, let's say 20 passes, maximum delta as 0.01, true converged passes, and we'll make the refinement 20%. Okay. And I don't want to have a frequency sweep because we just want to look at the fields at one frequency. So I'll delete this. Okay, that's it. Say setup, analyze. So while that's going on, what I wanted to show you is a file that I made. So this is a file that generates a grid file that we can directly use to extract the fields. So you remember, like in I think EM06L, the EM06L video, I showed you how to extract fields from HFSS, and there we had to actually define the grid in HFSS. But that's kind of cumbersome when you want to keep doing this for different sizes, and if you want to do it for all faces at the same time. So I just made a code essentially that can give you a grid file that will input into HFSS and then directly extract the field like that. Okay, so here essentially we want to set the same grid, -50 to 50, -50 to 50, and -10 to 130, right? So over there it was starting at -10 and it was 140 in size. So that's what this means. And okay, you extract the box limits, and then you can kind of go through how this code works. I'll provide this in the description below on my GitHub, so you can download these codes. Essentially, it provides an R prime vector, which is the position vector, and an n hat vector at each location of R prime. Okay, it builds that up, so you can kind of look at that, how that works, and then it exports it as a box underscore faces dot points file. And this is what HFSS likes to accept. And I'm also saving this R prime, n hat, and ds value, where ds is the size of the surface element. Okay, so I'll show you how to use that. So going back here, simulation is done. Now what I want to do is hit tools, say record script to file, and I'll say saving fields, hit save, and then we'll extract the fields. Calculator, export, and then I'll call this E field. And here last time we used this, but this time we'll use this input points. Oh, we need to create this points file. So go back in here and run this code. Okay, so once you run this code, it should create a points file. There you go. Right, so now we have this points file, hit open, and then just hit OK. Then clear, and then we'll use the H field, export output file name, call it the H field. And then again, we'll use the same points, hit OK, and then say done. Okay, and then stop script recording. So essentially, we made a script that every time I don't have to save the fields by going into the field calculator, I can just run that script. Right, so we'll see examples of that. So let's go back to MATLAB. Okay, so now we have our E field and we have our H field, right? So here's the code I've written out to extract those fields and then compute the currents. So the observation point I'm looking at is the E plane, which we looked at before in the near field. This is not the near field, but it's close. It's around 1 meter. So my observation point is there. So I load the fields. So this one, we can remove this part and this part, right? And then I also load this, the position in normal vectors. Okay, so maybe we can run this part of the code. Okay, so you see that you have the E field and H field. Then you can compute the complex field, compute the currents as n hat cross H and minus n hat cross E. And then we initialize these fields, E and H. So dg is for the Dyadic Green's function. There is this other one, SC, which is a Stratton-Chu version of computing the fields. That's a slightly different integral, which I also implemented here. And you can play with that if you like, and you can look up what that is, but they're equivalent. Stratton-Chu maybe is a little bit more numerically stable when you're very close to the currents. And this is actually what HFSS implements, but the Dyadic Green's function approach is basically the same. And for our purposes, both are equally good. Okay. So if you look at the Dyadic Green's function, let's open that up. So here I have the Dyadic Green's function, the currents. This is the source vector. This is the observation vector. ds is the size of each pixel, I guess, because we pixelated the surface. And then the frequency of operation. Right, so it's very simple, as I said in the video, that it's just a few lines of code. Calculate the R vector, calculate R and R hat from that. AR and BR are the coefficients. It's the free space Green's function. And then we calculate basically two coefficients for the two terms. And then we write out exactly that value. Right? And then you use the for loop to integrate over different points over the R prime vector. You don't have to run for loop. You can make this faster by vectorizing this. I did it this way just because it's a little bit easier, right? But if you actually want to do this for large surfaces and things like that, you should vectorize this for loop. Okay, so once you do that, then it returns the observed E and H. And that's what we have here for different points in the observation space at the E plane. And then what I've done here is essentially computed the norm, and then I'm plotting the norm and comparing it with the field I get from HFSS. So let's do that. So we'll create a near field setup, sphere from minus 180 to 180, 1 degree step, 0, 90, 90 degrees, and we want this to be at 1 meter. Hit OK. And then we'll create near field report, dv. So that's the H plane, and this is the E plane. Right, so I can export this as HFSS E plane, and this as HFSS H plane. Okay, save this. Let's go back to MATLAB. And okay, there you go, HFSS E plane, HFSS H plane. I hope that's the one that I just saved. Yeah, 735. And now we can run this code. Okay, let's see what it shows up. Should take a few seconds, not too long. Okay, there we go. So we see that they are closely related, right? Did I extract the fields? So I saved the grid file. And yeah, that's right. So this should be fine. Okay. So you see that they're very close in which plane is this? This is the E plane, and I'm plotting E plane here. That's right. Okay. Let's go back here. So you see that they're kind of close, but there is some disagreement here and here. Right. So we can also look at the H plane and compare. So let's go to figure 2. Maybe let me actually make this in blue. Okay, that's better. And then we'll say figure 2 and then do the H plane version. Okay, so you see in H plane, the agreement is also pretty good. There is some disagreement here and here, right? Close to 90 degrees. In the same way here, right? Okay, so it's pretty good, pretty good agreement. So the reason for discrepancy is that if we go back here, let's plot the mesh. And I hit face selection, plot mesh. Okay, so you see the way that HFSS has meshed this, it's quite different than the mesh that we are using, right? The one that we are using is a uniform grid over all of these points, and a uniform grid over all of these points and these points and so on, right? Whereas the mesh that HFSS uses, if I plot this side, so you see it's kind of a dense mesh here, and then a not so dense mesh out here, right? And if I plot the back, once again, not very dense, right? And that's really the advantage of using HFSS is that, it has a very good meshing tool. So it creates a dense mesh in regions where the fields are strong. Why does that matter? That matters because essentially when you make a uniform grid, you're weighting the edges of this region the same way as the center, right? So the solution that we get is sensitive to the field accuracy close to these boundaries where you have like this 90-degree change in surface direction, right? And there is an error that kind of exists on these edges, right? Because at this location, the normal vector is not really well defined, right? So you get a sharp discontinuity in the fields. And HFSS knows how to manage that, but the way that we have meshed it, it doesn't really manage that very well, right? So one way to get around that is to use a spherical near field. So computing the fields on a sphere inside the air box. So you make the air box very large. You can compute the fields on a sphere, which doesn't have these kind of discontinuities. But spherical near field has kind of its own issues, right? Near Z, there is a singularity. So you need to put the Z axis in a region where the field is very weak. So maybe in the negative, along y direction, and maybe you should put y hat along z, right? In your coordinate system, extract spherical near field in that coordinate system, and then take the far field, and that would be more accurate, right? But for this horn antenna, it's still not too bad. And the reason it's not too bad is because the horn antenna has fields that are very closely confined to this region. And you don't get much field that shows up close to these boundaries. Whereas if you try to do this with a patch antenna, you would not get that good results, right? Because for a patch, you need to put the face pretty far away from the radiating patch, and the radiation is from the ground plane, which radiates everywhere, right? And because it radiates everywhere, there's quite a bit of contribution to these edges. And then our approximation of using a uniform grid or a uniform mesh is not very accurate, right? So if you use a patch, you'll see that essentially you have to make the airbox very large. And when you make the airbox larger and larger, although the overall behavior will become closer and closer to what you have, but the contributions from these edges will start dominating, and then you'll get this ripple, high frequency ripple on top of your pattern. Okay, you're welcome to explore that if you like, but it's important to keep in mind that the mesh matters, right? The way you mesh it makes quite a bit of difference in the extracted fields. Okay, so that's kind of a quick demo. I just wanted to show you how you can essentially use these big equations. And in terms of implementation, it's actually pretty straightforward, right? So it's kind of handy to have these functions available to you. And of course, what you can do is you can also export the mesh and the fields over this mesh. So if you do that, then you can get pretty much exactly the results that HFSS has here, right? But I'm not going to demo that here, and you're welcome to try that. Okay, so we'll probably stop it here. It's a short video. It's kind of a useful tutorial on extracting fields quickly. So the reason I did the scripting is I can quickly demonstrate. So if I want to, let's say, do it at a different grid, minus 40 to 40, I just have to run this, and then I go back to HFSS. I go to Tools, Run Script, and I run this. That extracts the fields, and then I can just go back here and then run this, right? So that'll give me a solution for a slightly different mesh distribution. I didn't have to open the HFSS calculator, right? So that's why it's a little bit more helpful. Okay, so results look a little bit more accurate, but you're welcome to play with that. Okay, so I'll probably stop here. Hopefully you enjoyed that. I'll see you in the next one. Thank you.